Next, we will discuss how to do calculus with the hyperbolic arc cosecant of x function. Let's consider the hyperbolic arc cosecant of x function and let's find its derivative. Of course, we can try using the limit definition of the derivative, however, we'll get stuck quick. But let's not forget the alternative definition of the hyperbolic arc cosecant function, which is actually a piecewise function. So if we want to find its derivative, we have to do it twice, once for the right branch and once for the left branch. Let's find the derivative of the right branch of the hyperbolic arc cosecant function. We can use the chain rule, which is particularly easy when applied to the natural logarithmic function. Simplifying the expression produces a surprisingly nice result. Now, let's find the derivative of the hyperbolic arc cosecant function on the left side, using the chain rule, which is particularly easy when applied to the natural logarithmic function. Simplifying the expression produces a surprisingly nice result. In summary, we now have the formula for the derivative of the hyperbolic arc cosecant function for the left and the right branches. These two formulas can be elegantly combined into one by using the absolute value notation, which also makes it easy to write the formula for the antiderivative of the derivative. Let's, for example, find the derivative of the following function. We start the process by recognizing that we have to find the derivative of a composition of the hyperbolic arc cosecant function applied to the reciprocal function, which is equal to the following expression, in which we know how to find all the components. We get the final answer after plugging everything in and simplifying. Let's, for example, find the derivative of another function. We start the process by recognizing that we have to find the derivative of a composition of the exponential function with base 2 applied to the hyperbolic arc cosecant function, which is equal to the following expression, in which we know how to find all the components. There isn't much to simplify after plugging everything in. Let's do an example of an integral. We first recognize the pattern and rearrange the integrand. Then we set up the substitution by setting a new variable, let's say t, equal to the hyperbolic arc cosecant, and finding the differential of t. Next, we plug everything into the original integral, and notice how, because of the discovered pattern, we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function back for t. Let's do another example, but this time of a linear substitution. We set up the linear substitution by setting t equal to 4x and finding the differential of t and expressing dx in terms of dt. As a result, we have a simple indefinite integral in terms of t. We continue with the integration process by finding the antiderivative and replacing t with the original function. We discussed how to differentiate and integrate the functions that have the hyperbolic arc cosecant as one of their components.